We're asked which of AB, BC, and CA is a square number. So AB is going to equal P squared times PQ, which is P cubed Q. Now, these are both prime numbers. They don't share any common factors. It is not going to be possible to write it as something squared because I've only got one lot of Q, and actually I've got three P's times together. I can't get a square number, and the odd powers basically make it impossible. Let's take a look at BC. So for BC, I've got PQ times P cubed Q, which is P to the 4 Q squared. These are even powers, so I could write it as P squared Q all squared. BC is prime. Sorry, not prime, is a square number. Basically, whenever you have an even power, you can write it as a square number. Like 2 to the power 6 is necessarily a square number because it's going to be 2 cubed squared, which is 8 squared, 64. So we can have two numbers that are not square, times them together, and get a square number. Okay, it doesn't always have to be like 9 times 9. It could be 3 times 27, for example. And you can have different primes in there as well. So finally, I think we know the answer, but CA is going to be P, oh, not B, P cubed Q times P squared. I'm going to get P to the 5 times Q. This is not going to be possible either. Now, for part B, we're asked to place 9 of the 10 integers from 1 to 10 into the cells of a 3 by 3 grid in such a way that the three numbers within each row are written in increasing order from left to right, and the product of the three numbers within each row is equal to a square number. Give an example of how this is possible. Okay, going to draw the grid. A little bit smaller. So they have to go in increasing order from left to right, and when I times each row, I need to get a square number. Well, let's write down our integers. 1, 2, 3, 4. I'm also going to write them using their prime factors. That links into part A. 5, 6, which is 2 times 3, 7, 8, which is 2 cubed, 9, which is 3 squared, and 10, which is 2 times 5. So we saw before that when you just have, something like q by itself when you times them, there's no way it could be a square number. And because there's a 7 here, but there's no 7 anywhere else, whenever I times my numbers together, if I put 7 in, I'm just going to there's no way I could get 7 squared coming out of it. So I'm going to have to reject this one. Can't use. But the rest of them have got some, when you combine them together, we're going to get these combined factors. So the one that jumps out at me is 5 and 10. Because then I've got 5 times 2 times 5. And that's going to give me 5 squared. I'm going to get a square number. But I've got this odd power of 2 now. So I either need to times it by 2, because this would be 5 times 2 all squared, 100. Or I could actually do 5 times 10 times 8, because that one's 2 cubed. And then I'd get 5 times 2 squared. So these are two options, but I'm definitely going to have to, there's no other 5s in here, so I'm definitely going to have to combine the 5 and the 10, but then there's going to be two options for whether I use 2 or 8. Okay, we'll come back to that, because the other one that then jumps out is the 6 and the 9, because they've got factors of 3. I'm going to have to combine them together. So 6 times 9, I'm going to get 2 times 3 times 3 squared, Um, Sorry, I've just realized that's not going to work. I can't use that because that would give me an odd power. So forget that. In fact, we need the 3, don't we? Okay, because then I'll get an even power of 3. But I've got an odd power of 2, so I'm either going to have to times by 2, and that will give me 2 times 3 squared, or I can instead times again by 8, and that will give me 2 squared times 3 squared. So again, I have to combine the 6 and the 3 to get an even power of 3, and then I'm either going to use the 2 or the 8. So the question is, do the rest work? Are they okay? 1 times 4 times 9. Yeah, I've got actually when you times square numbers together, you always get a square number again. A squared times b squared is going to equal ab all squared. So this will work. Now there's not going to be any other possibility because I have to couple up the 5 and the 10 to get the even power of 5. I have to couple up the 6 and the 3 to get an even power of 3. And then I can either use 2 with this one and 8 with this one, or 8 with this one and 2 with this one. So that's going to be possibilities. And then I'm just left with using 1, 4, and 9. But that will work though. So let's just give one example of how it could work. We're told, remember, it has to go in ascending order. So let's put 1, 4, and 9 here. And then why not put 2, 5, and 10, which is going to leave me 3, 6, and 8. So that's going to be one option. In part C, we're asked how many grids can Howell produce. Okay, using B, we we can swap rows around. We could swap, I didn't do it in there's no reason why I did it in this order really. Just because I did 1, 2, 3, I could do 3, 2, 1, and so on. So I guess if you look at the first one, 1, 2, 3, how many different ways are there of arranging 1, 2, 3? Well, we could write 1, 3, 2, and that's it for 1 starting. But then I'm going to get the same for 2 starting. I'm going to get 2 lots. And then for 3 starting, I'm going to get 2 lots. And the answer is 3 factorial, or 6. There's going to be 6 ways of arranging. You can try and write them all out if you want. But we're not quite done. Because remember, we said that actually it could be 5, 10, and 8. So I need to look at those possibilities as well. So I'm gonna have to change this actually. So this will change to a 2, and this will change to an 8, but I'm gonna have to now rewrite them in ascending order. This just helps me do that. So again, 1, 4, 9, 5, 8, 10, 2, 3, 6. These will necessarily give me square numbers. I've shown it above. So another grid looks like this. Again, there will be 6 arrangements. Okay, as I swap them around. Therefore, in total, there are 12 possible grids. I've argued why we can't have any others, so I hope you're happy with that. Okay, really like this question. Hope you did as well.